recording. We'll go to, yeah, okay, it's recording, so whatever you want.
All right, perfect. Hello, everyone. I'm Ali Harakeh. I work with Professor Stephen Waslander at the Trail Lab. I'm hoping to graduate by May. I finished my PhD by May. And today I will be presenting my work on regression predictive distributions in deep object detectors. In particular, how to estimate and how to evaluate these predictive distributions. Object detection is a multitask learning problem where we need to classify objects, each object in the scene, and localize these objects with the tightest fitting bounding box. Object detectors have been used more and more as measurement inputs to components in a robot system or to algorithms in a robot system, including tracking, localization and mapping, and planning. Whenever we discuss measurement inputs, we want a notion of uncertainty associated with these measurements. And therefore, we need to perform probabilistic modeling. In fact, probabilistic modeling is the language spoken by most components of a robot system. My work for the past couple of years revolved around enabling object detectors to speak the language of probabilistic modeling. In particular, I investigate probabilistic object detectors, models that predict probability distributions for categories and bounding boxes simultaneously. Keeping up with my language analogy, not all sounds generated by humans are useful for conveying information. And it's the same with predictive distributions. Not every predictive distribution is meaningful. A predictor should output a low entropy, high confidence distribution when it makes small or no mistakes. And it should output high entropy, low confidence distributions when it makes large mistakes. This is important as, for example, overconfident incorrect predictions can lead to non-optimal decision-making in planning tasks, whereas underconfident correct predictions can lead to underutilizing information in fusion operations. The work I will be presenting today has been published in iClear 2021. Here's a link to the paper, and here's a link to the code. All the models and data sets and everything I'm going to be talking about has been open sourced, and the code is available at this link. The main contributions of this work is exposing the pitfalls of 3 common trends used to model, to do probabilistic modeling in object detection. Mainly, the exclusive usage of the negative log likelihood loss for learning predictive distributions. Also, the usage of a target assignment schemes during training that are detrimental for learning high-quality regression predictive distributions. And finally, the widespread usage of non-proper scoring metrics for evaluating predictive distributions in probabilistic object detectors. I will be explaining in details each of these 3 trends and their pitfalls. And it's worth to mention that we have solutions for the first and the third trend, but unfortunately, the second trend, we're still working on it. It's quite difficult to resolve. I will begin by formally defining probabilistic modeling for object detection and briefly discussing how modeling has been done in literature. I will then discuss the pitfalls of the 3 trends observed in literature and provide solutions for 2 of the 3 pitfalls. I will then end with some takeaways and recommendations for people who are interested in using my work. So again, object detectors perform category classification and bounding box regression. We will refer to the categories as Y in this presentation and the bounding boxes as Z. We will be working in 2D, so everything is in R4 in regards to regression. We are provided with a dataset D sampled from a joint conditional data generating distribution, P star. Here, X are input features. So there usually are some learned representations on images or point clouds if you're doing 3D object detection. We would like to use this data set to fit a parametric model, P theta, that best estimates P star, using only the samples provided in the data set, of course. In general, the category and the bounding box are assumed to be independent, although this is not necessary for the rest of the presentation. So The estimated parametric distributions are referred to as predictive distributions. For classification, we use a categorical distribution as our model. And for regression, we use a multivariate Gaussian distribution. Now, what do these look like on an image? Instead of point estimates for the category, we would like to estimate a probability for every possible class that could appear in our scene. For example, here we would like to classify each object to either dog or background. We have a probability associated with every class, which is a categorical, which is the definition of a categorical distribution. Similarly, instead of just estimating bounding boxes, we would like to estimate the mean of the bounding box distribution and a covariance matrix for the corners or for whatever representation our bounding box is. I will be showing the covariance matrices as 95% confidence ellipses around the corners in this presentation, but there are other ways to basically represent bounding boxes. So this is not exclusive. Given a data set comprised of samples from the data generating distribution, our network should learn the parameters of the classification and regression predictive distributions. The classification task has been studied extensively in literature. We can just use cross-entropy loss to learn a categorical distribution. For the regression task, which is the focus for the remainder of this presentation, the problem is a little bit understudied in literature. We try to resolve this problem by introducing proper scoring rules. So, scoring rule S is a function that maps a predictive distribution P of theta and the correct target Zn to a real valued scalar. S is said to be proper if and only if the only predictive distribution that produces the minimum value on S is actually P star. So basically, the only way that this has the minimum value is if we estimate P star, the data generating distribution. This is very useful, as we can now use proper scoring rules as a minimization objective as well as an evaluation metric. The most famous proper scoring rule for regression tasks is the negative log likelihood. We will be concerned with proper scoring rules that are negatively oriented. Basically, the lower the scoring rule, the better our predictive distribution matches P star. How did previous work tackle the problem of probabilistic object detector? Previous works followed a simple pipeline inspired by the work of Kendall and Gall. Basically, the pipeline says that to create a probabilistic object detector, you choose a deterministic object detector first, you extend it with a variance network, which is basically just a layer to estimate the covariance matrix, and then you train with the negative log likelihood, which is a proper scoring rule. Some of the works also decided to use dropout in addition to the variance networks, which is what Kendall and Gall do. But this is optional, not every work does this. The surprising thing is that unlike Kendall and Gall, which used proper scoring rules to evaluate their predictive distributions, probabilistic object detection uses standard deterministic detection metrics. They do not use proper scoring rules to evaluate their predictive distributions. They measure accuracy, and they make conclusions based on accuracy. By observing these trends, we ask ourselves three research questions. Are we guaranteed that training with negative log likelihood provides high-quality bounding box predictive distributions? Is it okay to simply extend deterministic object detection backends with variance networks and create probabilistic object detectors this way? And finally, is it enough to verify the quality of predictive distributions using non-proper scoring rules? The answers to these three questions is no. I will begin by describing the pitfalls of training with the negative log likelihood loss for learning bounding box predictive distributions. As a reminder, we will be focused on bounding box multivariate predictive distributions. We are given a sample Zn from the data generating distribution, and we have a network that outputs a predictive distribution parameterized by the mean and the covariance matrix. we can evaluate how much probability is assigned to Zn by our predictive distribution using the negative log likelihood. Since the negative log likelihood only considers probability assigned exactly at Zn, it's called a local proper scoring rule. What does locality intuitively mean? We look at the negative log likelihood at a single dimension. Given two distributions, one that has a high variance, incorrect mean, and one that has a low variance, but a more correct mean, which of these two would negative log likelihood prefer? The answer is the high variance incorrect mean one. Why is that? Negative log likelihood is simply the negative of the log probability. If we estimate if our mean estimate is very correct, but our variance is so small that no probability is assigned at Zn, our negative log probability will be infinity, right? Because we will have zero probability, so negative log of zero will be infinity. This is clear from the denominator containing the variance here. Now, why is this problematic? This is problematic because negative log likelihood tends to penalize more confident distributions much more severely than less confident ones. To show this, we create a toy example in context of object detection. We generate two sets of detections, one with low errors and one with high errors. We will be using IOU to measure the errors intersection over union. Basically, high IOU means low errors in detection context, and low IOU means high errors in detection context. We then assign an isotropic covariance matrix with a parameter sigma to both sets of detections. And we compute the negative log likelihood and plot it as a function of sigma. We see that negative log likelihood, even for the correct set of detections, it penalizes low entropy distributions much more severely than high entropy distributions. We will show that this is problematic when training variance networks for object detection. But first, we would like to introduce an alternative for the negative log likelihood, the energy score. The energy score is a non-local, distance-sensitive proper scoring rule that is independent from the exact form of the predictive distribution. Basically, the energy score depends on independent samples from the predictive distribution, as well as the ground truth sample from the data generating distribution. Now,
what do you mean by non-local here?
I will explain that non-locality. So, okay, let me take 1 minute to explain non-locality.
If you are going to explain that, it's fine. Carry on then.
Yeah. We'll explain what this distance sensitivity means and non-locality means here. So, considering our previous toy example, we noticed that the energy score, which of these two would the energy score prefer? The energy score prefers case number 2, the low variance one with the correct mean. This is because the energy score is non-local and distance sensitive. By non-locality, we mean that the energy score does not only take into consideration the probability assigned exactly at the ground truth target, but also but rewards distributions that assigns a high probability mass near the target, but not exactly at that target. And this is what's called non-local proper scoring, basically. So as an analogy in classification, the Breyer score is not local because it takes into consideration all the parameters of the categorical distribution. So looking back at our toy example, the energy score acts in an opposite manner to negative log likelihood, penalizing high variance distributions much more than low variance ones. This is because the energy score is what we call the distance-sensitive non-local proper scoring rule. It rewards distributions that assign high probability mass near the ground truth target, even if not exactly at the target, and even if zero probability is assigned exactly at the target. As long as we're near that target, we're good to go. The energy score is not just an equation that we decided to use. It is theoretically founded with moment matching capabilities. In fact, it is shown to be equivalent to the maximum mean discrepancy. Basically, it's only zero if the ground truth if the predictive distribution is exactly equal to the data generating distribution. So, what does this all of this intuitively means in context of object detection. The energy score, basically, let's say we have two sets of detections, one with very high entropy and one with very low entropy. The energy score would prefer the one with the low entropy as long as the mean estimate is somewhat correct. Whereas the negative log likelihood would penalize these distributions quite severely because there's no probability or very little probability assigned exactly at the corners. We argue that this case is better for object detection than this case. And we show the manifestation of this property of negative log likelihood when used for training. So we perform the following sets of experiments. We take 3 deterministic object detectors, Dept, RetinaNet, and faster RCNN, pretty famous Detectron 2 API for object detection, and we extend these with variance networks. We then train with either the negative log likelihood or the energy score. The resultant is 6 probabilistic object detectors. For training, we train on the COCO dataset, and we test on both the COCO dataset and the open images dataset. Why is that? Because we also want to observe our performance under dataset shift, and if we can learn anything from that performance. We start our evaluation using non-proper scoring rules first, and we observe that for Dept and RetinaNet, the energy score provides a much better calibrated, this is regression calibration error, a much better calibrated predictive distributions than the negative log likelihood. However, for faster RCNN, the results are mixed. It's inconclusive. Why does this happen? Basically, just as a note, these both accuracy and regression calibration error are not proper scoring rules. We will discuss the proper evaluation later on. But for now, we just were interested in seeing why faster RCNN has mixed results with the negative log likelihood. To do so, we dig deeper and plot the entropy versus IOU plots on the COCO dataset. Basically, the x-axis here is high error to low error. It's 0 IOU to 1 IOU, high error to low error. And the y-axis is low entropy to high entropy. We see that negative log likelihood provides much higher entropy distributions when used with Dept and RetinaNet, and provides almost equal entropy distributions when used with RCNN. On the other hand, the energy score does not change, its entropy does not, the average entropy at least, does not change much between architectures. We verify this visually. We plot the results from Dept trained with negative log likelihood and Dept trained with the energy score. Here, I'm not sure if you can see this, but the green boxes here are the ground truth. Our mean estimates almost overlap with the ground truth. However, the negative log likelihood still predicts very high entropy distributions when trained with when used with Dept. When used with RCNN, this is not the case. We want to understand why this is happening, so we dig deep. We dig deeper into the reason for this, and discover that this is founded in how object detectors train during or evaluate the regression loss during training. This is referred to as regression target assignment. So we need to state 2 facts about object detectors first. Detectors evaluate their regression loss on only a selected subsample of their total predictions. These are called positive detections. Usually, what determines a positive detection is the error. However, there is no consistent definition for positive detection. Each architecture uses a different definition of positive detections. We plot what the errors of positive detections are as training progresses. So here, these are called violin plots. These are the distributions of the intersection over union with the ground truth of regression targets. Basically, the network selects some predictions to evaluate its regression loss. This is the error in these predictions. We notice that the negative log likelihood generates high entropy distributions when the network is trained on low error regression, or low IOU, high error regression targets. Basically, by restricting your training regression targets to only low error ones, high IOU ones. Basically, if we train the network to only evaluate the predicted distributions, or to predict the predictive distributions on small mistakes, we get the correct, or we get low entropy distributions from negative log likelihood. However, when we allow it to observe higher error targets, we get very high entropy. So basically, training with high error regions manifests the preference of negative log likelihood for high entropy distributions. The question is, can we just use what RCNN is using, restrict the training to low error regions, and train with the negative log likelihood? Then we will avoid using energy score. We don't need to use energy score. The answer is not that simple. And this has to do with the notion of meaningful predictive distributions. What we notice is that for predictive distributions to be meaningful, they need to be correlated with the error, right? So high error regions needs to have high entropy, and low error regions needs to have low entropy. When we observe the plots of RetinaNet and RCNN, we notice that this is not the case. In fact, at the extreme case of RCNN, very high error outputs have a much lower entropy than very correct outputs. And this is pretty not meaningful in a robotic, in the sense of when we consider it for robotics tasks, right? You're saying that the high error mean estimates have a lower variance than the low error mean estimates. Why does this happen? The answer comes in a recent paper from Europe's 2019, where variance networks are seen to not be able to capture the poor mean estimates outside the data support. Basically, if a network does not observe the whole range of available errors during training, it cannot correctly predict the correct distribution during inference. And unfortunately, a very efficient way to restrict your data support during training is to only train on good detections or on very low error detections. The question that I asked myself after realizing this is, what about the actual other differences in architecture? Like, what if Dept has done something else that resulted in better predictive distributions? To answer this question, I did a controlled experiment. Basically, we take faster RCNN, we train it with the energy score, and we restrict the data support at various error thresholds, IOU thresholds, of 0.1, 0.3, 0.5, and 0.7. So 0.1 allows the network to observe the most of the range of errors, whereas 0.7 does not allow the network to observe anything below, let's say, 0.7 IOU. What's the resultant of this? We see that we can actually fix the entropy versus IOU plots by increasing the data support during training. However, the solution is not as simple as just reducing the IOU threshold during training, which is a parameter you can change in the config file. This is because most networks are built on these hyperparameters, and changing these hyperparameters results in a huge reduction in performance on accuracy. In fact, we noticed a drop of almost half when we use 0.1 IOU as a threshold for choosing our regression targets. We haven't found a solution to this problem. We are still working on trying to solve this problem, but this is a substantial problem in probabilistic object detection that needs to be resolved. For now, we recommend using Dept as a backend for probabilistic object detection, because the way it chooses its regression targets is that it allows the whole data support, choosing regression targets across the whole data support, while at the same time having a high enough average precision. The final thing I would like to discuss today is the pitfalls of evaluation. This will be quick. I will not be emphasizing on this, but a full argument is available in our paper if you would like to read that. What we noticed is that most of, or all, literally all probabilistic object detectors available in literature consider non-proper scoring rules as their metrics to evaluate the quality of their predictive distributions. In machine learning, however, we routinely evaluate the quality of predictive distributions using proper scoring rules, Why not do that in probabilistic object detection? We devised an evaluation protocol and presented it in the paper, founded on proper scoring rules for classification and proper scoring rules for regression. I will not be describing this right now, but I will be explaining why we need both energy score and negative log likelihood, or local and non-local proper scoring rules for evaluation. To do so, we repeat the same six, we use the same 6 networks presented above, basically Dept trained with negative log likelihood, Dept trained with the energy score, RetiNet negative log likelihood, and so on. And we evaluate their performance using the mean squared error, the negative log likelihood, and the energy score, because these are proper scoring rules and they can be used for training or for evaluation. The first thing to note is that networks provide the same mean squared error. That means when the proper scoring rule changes, it's because of mistakes or because of changes in the covariance estimates and not in the actual mean estimates. We notice that evaluating with negative log likelihood is biased towards high entropy distributions. We showed this before, right? The negative log likelihood prefers distributions that assign a probability at exactly at the ground truth target. So when your distribution has very low probability at the ground truth target, it will have a very high negative log likelihood. But this is not very, basically, this might cause misleading conclusions. Why is that? Because the network can make sure that it gets a constant negative log likelihood just by increasing its variance to substantially high values. And this is evident here. When we use the negative log likelihood to evaluate Dept NLL, it has a constant negative log likelihood. Whereas Dept ES actually starts substantially increasing its negative log likelihood. This is because Dept ES provides much lower entropy distributions, and as such might not provide the probability exactly at the corners. When we use the energy score, however, we notice that the problems or the drawbacks of having very high entropy distributions is evident. Basically, our distributions are so high entropy that from Dept negative NLL that it has substantially higher energy score than Dept ES. In general, we recommend that you use both to evaluate, and the full evaluation protocol again is in the paper if you're interested. I will end with some takeaways and recommendations for people who are interested in object detection and for the general audience. The first take-home message is that not all proper scoring rules are equal. The energy score is better suited to be used as a minimization objective for learning bounding box predictive distributions, and it might be useful for training variance networks in your own application that requires multivariate regression. Some of my lab mates are already using this, and it has been shown to be more stable than the negative log likelihood, and it produce better results than the negative log likelihood on other applications than object detection. We also need to rethink how we train object detectors if our goal is high quality predictive distributions over the full range of data support. And for your own application, I would recommend that you take into consideration the data support during training when using variance networks, because variance networks have a limitation and cannot produce proper outputs when they are not exposed to the data support during training. And my final recommendation is, if your application has been using accuracy-based metrics for evaluation and you decide to transform it or do probabilistic modeling, you will need to use proper scoring rules for evaluation. Using accuracy-based metrics are not descriptive and might lead to misleading conclusions. Thank you for listening to my presentation, and I really hope that you learned and benefited from this, from my work.
No, this was wonderfully done. I think this was, first of all, to begin with, very insightful, this idea of energy score. Rather, what I would say is, I would not have thought about this, the way you found the results to be very sort of different. I'm curious, this idea of because negative log likelihood is so broadly used across unsupervised learning, evaluating any sort of uncertainty of the model. I'm very curious, the problems that you highlight with negative log likelihood, are they exacerbated in other domains then, or would they be exacerbated in other domains that are not, let's say, simple detection? That's first question. And is energy score universally better? In your results, you notice that it was better in some data sets, it wasn't better in some data sets, and you probably have hypotheses for this as well. So maybe you can comment on that.
So the first thing I would like to say is that both energy score and negative log likelihood are proper scoring rules. In theory, at the limit, if you have infinite data, any proper scoring rule should be able to retrieve your data generating distribution, right? The problem is that our data sets are not perfect, and our estimates are not perfect, and our optimization is not perfect. That's why the energy score was shown to be beneficial in this case. So to answer your first question, yes, negative log likelihood has been used in many other applications, right? What we noticed is that depending on the application, it will either result in exactly the same performance as the energy score or worse performance. We also noticed a substantial difference in stability during training. So if you look at the energy score, let me go back to the energy score equation and give you some more insights, because this is important actually, and I didn't have time to add it to the presentation. So if you look at the energy score is very stable, because if you have zero variance, your energy score will just reduce to the mean squared error, right? So if you have zero variance, this term will disappear. Your samples will be all the same. Let me go back here, it's better here. So these are samples from your distribution. These will be all the same. The difference in samples will be zero. And all your samples will be the same, and the Zn is constant, it's a single value. So this will be just your Euclidean distance, basically. So this is much more stable during training than the negative log likelihood, which has dependence on inverse of your covariance matrix and log depth, right? But at the end, both are proper scoring rules. Both should retrieve your data generating distribution, but because of our inefficiencies during training and during inference, these have different performance. And your second question, can you repeat your second question? On data sets, yeah, I remember now.
So yeah, I was trying to mention in the sense that exactly. So one intuition on what data sets, where this might be sort of different.
We found that this is in terms of object detection, the energy score is a reliable go-to. Basically, it either works similarly to negative log likelihood based on the detector itself, right? Or works better than the negative log likelihood. And this is done on the COCO dataset, corrupted versions of the COCO dataset under dataset shift, and the open images dataset, right? So for detection, I would recommend that you just use the energy score. We tested the energy score also on toy examples on sinusoidal data, and it still outperforms negative log likelihood by a substantial margin. And we tested it on predicting paths for quad rotors. And the work is still in progress, but from what I've last heard, this is not my work, this is one of my lab mates, it also is more stable and provides better results than negative log likelihood. It's very simple to code, so it's worth a try. But like I noticed that it always gives you at least the same performance as negative log likelihood. I hope that this answers your question.
Yes, it does. I think Kevin has other questions. Kevin, do you want to sort of unmute, or should I just go ahead and? Okay, so Kevin asked, the ES distance or the energy score seems related to the Wasserstein's distance. Could you comment on the connection first?
The energy distance seems to be related to the Wasserstein distance, yes?
Yes.
That's the question. Yeah. Actually, the energy distance is an integral probability metric. So it's very related to the Wasserstein distance. It's not so to measure distances between probability distributions or to measure similarity between probability distributions, we can either use F divergences, like the KL divergence, or integral probability metrics, like the maximum mean discrepancy or the Wasserstein distance. The energy score is derived from the energy distance. which is a maximum mean discrepancy, equivalent to the maximum mean discrepancy. So it's very related to the Wasserstein distance, and it basically has the same mode of action as the Wasserstein distance, right? But the benefit of the energy score is that it's evaluated from samples. So we don't need access to distributions. We can to the data generating distribution. We can evaluate it just from one single sample from the data generating distribution. That's the benefit of the energy score. But yes, you have a point. Yeah, it's actually very related to the Wasserstein.
A follow-up question that Kevin has is, how would you generalize this idea to, say, non-Gaussian distributions?
Let me go back to, can you see my presentation?
Yes.
Okay,
yes,
perfect. Yeah. Let me go back to this here. Okay. So the energy score has been, how can you generalize this to non-Gaussians, right? The only problem I see, so the energy score is not defined in terms of any distribution, okay? The energy score is defined in terms of samples. So as long as you can have a differentiable sampling, such as PyTorch distribution API, to sample from your probability distribution, you can evaluate the energy score. What's the problem? The problem is that these expectations have a solution for non-Gaussians, but it's very computationally expensive to compute. For multivariate Gaussians, you have simple and very fast Monte Carlo approximations that you can use for these expectations. And this is in the paper if you're interested to do that. But other works before this, I think a work on from 2015 has used the energy score without any assumption on the distribution. Basically, it had a network that it generated these samples, and they computed the energy score, although it's very slow to train and it's computationally expensive, they computed the energy score without any Gaussian or multivariate Gaussian assumption whatsoever, right? So you don't need, the energy score is defined for any probability distribution. You might have computational issues while coding it, but there's no theoretical problem for generalizing this. Okay, there's questions in the chat. Should I read the questions in the chat or?
Oh, I was reading them
okay,
for you.
Perfect. Yeah.
Anybody else has a question? Chris, Mayank, Dhruv? I have one quick question. So I know you were planning to, of course, move on and graduate, but do you plan any follow-ups for this line of work for other domains or other perception tasks?
Yes, and we have a lot to do in terms of probabilistic extensions of classical computer vision tasks, right? My first priority right now is solving this issue. The issue with the training data here, right? This is my top priority right now. This is because we have provided ways to actually estimate the distributions, and we found that these distributions are nice and everything, but still the trends that exist are not very good. Basically, when we have such trends, we can't use the output of our object detectors in robotics tasks. So this is my first main task right now. That's not in my thesis. My thesis is done basically, but my task past the thesis, as long as I stay in my current lab, is to fix this issue. I'm working diligently to fix this issue. The additional extensions. We are working right now on some basically predicting the state of quad rotors using MLPs, and we want to predict a probabilistic state for quad rotors. So this is also, I'm helping one of my lab mates do this, and we're adapting the energy score for that. Additional tasks such as, let's say, segmentation or 3D object detection are also of interest, but I haven't looked at other ways. I would say I would solve this problem, and I would like to move on to some other stuff. I'm interested in lifelong robot learning right now. That's my main interest, shift from object detection. So it might just be this that gets completed for probabilistic.
This was also the work that got into iClear, or was this related?
Yes, this is the work that got into iClear.
I can imagine. Wonderful.
Yeah.
I actually have another question if you have time. I was wondering if you're aware of any works that do like non-Gaussian distributions, like multimodal distributions, and do they find any benefits from that, or?
For probabilistic object detection, you mean, or for the general?
Yeah.
There are. So the main issue with literature in probabilistic object detection is that the majority of literature uses mean average precision as their metric to discuss stuff about their predictive distributions. Yes, there is a paper in IROS last year that used multimodal Gaussians and showed that they gain on accuracy. But it was not shown if the gain actually translates to when using proper scoring rules for evaluation, right? So yes, if you want accuracy, it has been shown that multimodal Gaussians actually outperform univariate Gaussians, and they argue why regarding the bounding box corners and stuff like that. But I would actually be careful about looking at results from works that do not use proper scoring rules for evaluation. And this was one of the main contributions of our iClear paper, is that we wanted to basically make object detection go back to evaluating using what ML has been evaluating, which is proper scoring rules. Regarding the the full covariance matrix versus, let's say, diagonal covariance matrix, I found it to be a hyperparameter. Depending on the run, you might get better results with the full covariance matrix, or better results, like if you want to generalize your Gaussians, let's say, right? There is one paper that used a Laplacian instead of a Gaussian, but also the results are on MAP. So I can send you these papers, but I'm not sure that the results are conclusive, whether there's a substantial benefit from switching from a Gaussian or not. So.
Right. Well, one more question. So is there any downstream task that would be easy to, like a standalone downstream task that could be easily used as an evaluation metric, maybe to see how well ES correlates there? I mean, object detection is pretty standalone itself,
yeah,
but
yeah. That is one of the issues that are currently in literature. So the major issue is that we found that like object proper scoring rules are nice and everything, but also we need to evaluate in context of a full robot system, right? Now the issue is we tried to get the tracker, probabilistic tracker from some work, some published work, and they just replace the covariance. Basically, they have fixed covariance matrices that they pre-process from the training data. We replaced them with our neural network, and the results weren't that different, because apparently the methods that are designed previously are not sensitive to errors in covariance. Like you can have errors in covariance, but you still have good tracking, right? So this is something for future work. To do this to use other tasks as evaluation, you need tasks that can actually exploit your uncertainty. What we found out is that most of the tasks either are insensitive to uncertainty, the ones that we tested, of course. We didn't test everything. We tested tracking and a couple of other small stuff in tracking. So it is important, but we could not find a trivial way to do this without actually doing the work ourselves and designing the tasks to use our uncertainties ourselves, right?
Right, because I feel like in most cases, people only use object detection as a way to get a rough box, and then they would do something on top of that, right? Like a 6D pose estimation or something else.
I'm not sure if I have the knowledge to argue whether this can use our uncertainty estimates or not. But what I can say is that tracking and SLAM, for example, SLAM that uses objects as landmarks, should benefit from this work, right? We haven't done tests, to be honest, because it's just way too time consuming to do these tests, right? So
right, of course. And then are you aware of like the works from Yaron Gal and sort of.
Oh, yes, the dropout stuff, right?
Yeah,
Yeah.
so the question of the aleatoric versus the epistemic.
Very good question. This is a very, very good question. So the main paper that discusses aleatoric versus epistemic is what we mentioned here. It's Alex Kendall's work, right? This work from 2017.
Yeah.
So this is the main work that mentions aleatoric versus epistemic. In the same work, in the final conclusion, they found that if you estimate one of the two, you end up with the properties of the one that has not been estimated, incorporated in your estimate, right? So if you estimate aleatoric only, it shows similar trends to what would have happened if you estimated epistemic. You cannot disentangle these two, what I found. I tried it, dropout and ensembles actually, with object detection and found no benefit whatsoever. In fact, I found that variance networks, and this is in my iClear paper, if you go and see the last section of the iClear paper, variance networks by itself, which is supposed to estimate aleatoric uncertainty, can detect out of distribution regression targets. If you go to the last plot, maybe I can, I'm not sure. Would you like me to show you right now, or you're good?
That'd be cool.
Yeah, let me show you right now. Let me quickly stop sharing just so that I can pull my paper. Yeah, this is actually quite important, and this I suspected reviewers to actually ask about it, and they did. This was one weakness of the papers, and then I had to re-explain it, why this is happening. All right, so let me share my screen again. Can you see my screen? Yeah. So these plots are taken from mistakes. So basically, we collect our mistakes from an object detector, basically object detections that do not have any object in the ground truth set. And we plot their entropy, the distribution of their entropy, right? And here we have three data sets. In distribution, data set shifted, and the full out of distribution data set. We notice that our variance networks, which are technically estimating aleatoric uncertainty, can in fact distinguish between in distribution, shifted, and out of distribution instances, which is quite surprising because this is technically the job of the epistemic uncertainty, right? To detect out of distribution targets. So again, I don't think that there is a clear distinction in that we can basically disentangle the two types of uncertainties explicitly. So we just showed the results of variance networks in this work. But I have for the same results for dropout and ensembles, and they did not show any difference in results than regular variance networks. Maybe a slight improvement, very, very tiny. It does not warrant you going and training 10 ensembles for this is the improvement that we got. So yeah, we considered that, but it didn't show any improvement, so we avoided mentioning it in the paper.
That's very interesting. Cool. That's a bit unintuitive from other people's results on other domains, but perhaps they didn't.
I agree. I think
variance properly, maybe.
Yeah. I'm also sort of like, it's not just the depth of the results; it's the surprising nature of the result that is sort of very, very interesting to me. In any case, I think we're closing towards the end of the time. I would like to thank Ali for one wonderfully prepared slides. I think, regardless of the content, I really like the way you prepared the slide and the presentation.
Thank you so much.
Very well done, and also for the time that you took to explain and discuss. I think the format worked out very well, that we actually got a chance to actually discuss. So we would like to thank you for doing this. If you do agree, then we will sort of edit this and put the talk part online.
Yeah, that's fully okay with me.
Yes. Yeah, love to stay in touch. Hopefully,
Thank you so
for
much, Bob.
potential
Yeah,
follow-ups, and just let me know regardless how your job goes.
Thank you so much. If you guys have any question about this work or my previous work, I've been working on this for the past 2 years and I have several papers. Just feel free to shoot me an email. I'd be happy to meet with you and discuss this. Or if you want to extend the energy score to any other problem, I'll also be happy to discuss this with you and give you intuitions on implementation stuff and stuff like that. So just let me know. Thank you so much.